The present problem simulates the performance of a PCM in a circular chamber with a glass cover. The two-dimensional geometry of the model is designed using Design Modeler software. Also, the meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. We perform a pressure-based solver, so the gravity effect on the fluid is ignored. From the scale mesh section, we can check the direction in all three dimensions and also view the length unit that is meter in the CFD simulation. In the viscose model, the standard K epsilon model has been used. That is a two-equation turbulence model that allow the determination of both a turbulent length and time scale by solving two separate transport equations. The standard K epsilon model is in ANSYS FLUENT, falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K epsilon model is a model based on model transport equations for the turbulence kinetic energy K and its dissipation rate epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K epsilon model is therefore valid only for fully turbulent flows. The simulation is about phase change materials, so the solidification and melting module should be activated. Here is the PCM properties, and also the most important parts are pure solvent, melting heat, the solidus temperature, and also the liquidus temperature. And here in this section, we can check the glass properties, including density, CP, and thermal conductivity. Port glass is the solid zone. Also, the operating pressure is equal to the atmospheric pressure in the operating conditions section. The inner wall is a wall that from one side is connected to the glass part and from the other side is connected to the fluid or PCM. So the thermal condition of these kinds of walls is coupled. Also, for every coupled wall, there is a shadow boundary condition that the Fluent software make it automatically, and all the boundary conditions are equal. Setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS FLUENT, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. This magnitude shows that the initial phase of the PCM at the start point is solid. After just one time step that is equal to 600 seconds, we stop the simulation and check the contours. Here is the temperature contour that we can see. The outer temperature, as we mentioned, is equal to 338 degrees of Kelvin, and also the PCM initial temperature was equal to 332 degrees of Kelvin. And if we are going to obtain the exact magnitude of the volume fraction existing in the circular chamber after 600 seconds, you should follow this method from the surface integral, area weighted average, and the field variable of solidification and melting, also the volume fraction. A summary of the defining steps of the problem and its solution is given in these tables as a review. Obtain the mesh file and also the full training movie by purchasing this product. This PCM is evenly distributed inside the chamber. Due to the fact that the nature of the PCMs of the present model is based on the phase change between solid and liquid phases, solidification and melting model has been used for the simulation. PCMs are materials with inorganic or organic compounds that are capable of absorbing and storing large amount of latent thermal energy. Thermal energy storage in these materials is achieved during the phase change process, solid phase to liquid or vice versa, so that when the phase changes from solid to liquid, they absorb heat from the environment, and when the phase changes from liquid to solid, they return the heat to the environment. Of course, latent heat in phase change materials is obtained from three modes of solid-solid, solid-liquid, and solid-gas phase changes. But since the solid gas state, in the solid gas state, a lot of heat or pressure is required, and the solid-solid state is very slow, so most phase change materials are in the solid-liquid state. These phase change materials have different melting or freezing temperatures. Therefore, PCM is used in heating and cooling systems. For example, these materials receive ambient heat on a hot day in the form of latent heat and melt, and then in the cool air of the night return the heat to the environment again by changing the phase and solidification process. For the present modeling, a glass coating around the chamber containing phase change material with a constant temperature of 338.15 degrees of Kelvin has been used, which is responsible for transferring heat to the phase change material. The PCM in the initial state of simulation at 332.15 degrees of Kelvin. To use the solidification and melting model, the maximum temperature at which only the solid phase exists, or T solidus, the minimum temperature at which only the liquid phase exists, T liquidus, and the latent heat of solvent melting in the pure state, pure solvent melting, must be used. Because the simulation process is transient, the simulation performed in a time interval of 250 minutes with a time step of 600 seconds. The two-dimensional geometry of the model is designed using Design Modeler software. The present model includes a circle with an outer radius and also an inner radius as a circular chamber thickness. Also, the meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.